Hello dear students, welcome to YouTube channel of Unique World Education. This is Fazlur Rahman, Chemistry faculty of Unique World Education. I hope all of you are doing great. Today we are going to solve a question paper from grade 11 Organic Chemistry, which was recently conducted by a school from Dubai, Global Indian International School Dubai. I hope all of you have a basic idea about Organic Chemistry chapter, grade 11 Organic Chemistry. The first chapter of Organic Chemistry, basic concepts of Organic Chemistry and purification techniques. So we can solve this question paper. I will make you clear the concepts by doing these questions. Okay. So we can start. I hope all the Organic Chemistry basics like nomenclature, electromeric effect, okay, resonance effect, all these effects are very clear for you. So anyway, we can start doing the questions. Okay. Coming to the first question, coming to the first question, the displacement of electrons in a multiple bond in the presence of attacking reagent is called. So I hope all of you know there are four important displacement effects according to your syllabus. One is hyperconjugation, then inductive effect, resonance effect and electromeric effect. Clear? Out of that, the displacement of electrons in a multiple bond in the presence of an attacking reagent. You know, out of these four effects, which effect is produced only in the presence of an attacking reagent? I hope all of you know what is an attacking reagent. Attacking reagent means that can be either a nucleophile or an electrophile. Okay, so which comes to attack or which comes to join a particular hydrocarbon or organic compound. So which is that effect? So that is electromeric effect. So electromeric effect only occurs in the presence of an attacking reagent. Okay, so like this, for example, a double bonded carbon is there, a double bonded compound is there. So in the presence of an attacking reagent, for example H+, so one of the multiple bond will shift to one of the carbon, completely that electron pair will be shifted to one of the carbon. So this carbon will get a negative charge and this carbon will get a positive charge. Okay, so the H plus will join this particular carbon. Okay, so this type of effect is called electromeric effect. So there are two types of electromeric effects. I hope all of you know that, plus E effect and minus E effect. So this comes under plus E effect. Why? Because the electron pair is shifted to this particular carbon and the attacking reagent is also joining the same carbon. So that is plus E effect. So I hope that's clear. So the first one answer is option B, electromeric effect. Okay. So we can move to the second one. Homolytic fission leads to the formation of nucleophile, carbanion, free radical, carbocation. So what is homolytic fission? Homolytic fission means if the bond is breaking in such a way that each of the component elements, participating elements, get one of the participating electron, one of the shared pair of electron. So if this bond break in such a way like this, for example, A is getting one electron, B is also getting one electron. What is this? These are free radicals. Free radicals are having unpaired electron species, unpaired electrons, and they are highly reactive. Okay, so the answer is free radical. Okay, I hope you know the other one, that is heterolytic fission, which forms carbocation, carbanions and all. Okay, so we can move to the next one. Third one, the IUPAC name of CH3 CH double bond CH, C triple bond CH. Okay, so it's a very important question. We can discuss that. Just wait. Yes. Okay. CH3, I'm drawing the structure again here. Listen. So CH3, CH double bond CH, single bond C triple bond CH. Okay. So here you have two functional groups, one is double bond and the other one is triple bond. Okay. According to the priority list, double bond is having more priority than triple bond for naming, okay, for nomenclature, but numbering you have to start from which side? This triple bond side. That means wherever the multiple bond is present, you have to start numbering from that side. Okay, but while representing the name, you have to represent alkene first, ene first, then Y. Okay, that's the rule. So you have triple bond at right hand side, right end of the molecule. So you can start numbering from this side. Okay, 1, 2, 3, 4, 5. This is the numbering. See, it's very important to assign numbers to carbon atoms while naming organic compounds. So always please make sure that you are giving proper numbers to carbon atoms. Okay, otherwise you will lose the mark and otherwise you will be confused for nomenclature also. Clear? So now you can name easily. So how many carbons are there? What is the word root? Pent. Okay, so pent, then hyphen, then what? You have to represent the name of alkene first. Okay, alkene first. So double bond is on which carbon? Third carbon. Okay, so pent 3-ene, 3-ene, then which one? Where is the triple bond? Where is the triple bond? That is on first carbon. So 1-ine, 1-ine. This will be the answer. So we can check. Yeah, option A, pen 3-ene 1-ine. Okay, pen 3-ene 1-ine will be the answer. Got it? All of you clear? Okay, great. So I think it's clear. We can move to the next one. Fourth one, question number 4. Question number 4. Which of the following can act as an electrophile? Which of the following can act as an electrophile? What is an electrophile? So I told you, attacking reagent. Okay, electrophiles and nucleophiles are attacking reagents. So what exactly you mean by an electrophile? Electrophile means electron loving or electron seeking. Okay, so electron loving means that should be electron deficient. So that will be mostly positively charged ions or electron deficient compounds. So you can easily pick out from the options because there is only one positively charged ion is given in the option, that is NO2 plus. Okay, so NO2 plus will be an electrophile. Cn minus, OH minus, H2O, all that are what? Nucleophiles. How water is acting as a nucleophile? Water has lone pairs. Okay, so water will donate that electron pairs to any electron deficient species. Clear? So NO2 plus is the answer here. So remember, always positively charged ions will act as electrophile and negatively charged ions will act as nucleophiles. Got it? Yes. Now we can move to the next question. I hope the questions we discussed so far it's clear. Okay, next one. The purification method where solids changes into vapors without, just wait. Yeah. Yeah, okay. Uh, Actually, that portion is cut from this PDF. Okay, so that question was like, I will give you the question. The purification method where solids change into vapors without passing in without passing through liquid state. That was the exact question. Okay, so I hope all of you know that. You know the phase transition from directly from solid to gas. Directly from solid to gas. What is that called? That is sublimation. Sublimation only. Okay, sublimation. I hope all of you know that. That was the answer for this question. Okay, so now we can move to the next one. Yes. Okay, so now the very important questions are coming. We can solve that. Okay, question number 6. Mention the hybridization of carbon and shape of the compound. The marked carbon atoms you have to check. Okay, so first of all I will give you an idea about how to check the hybridization of carbons in organic compounds. I hope all of you know that, still you can listen. If all the carbon atoms are if all the valencies of carbon are satisfied by single bond, okay, if all the bonds are single bonds around a carbon, that carbon will be sp3 hybridized, sp3. Okay, if a double bond is present, that will be sp2 hybridized, sp2. And if a triple bonded carbon, or if on both sides of the carbon double bond is present, this too indicate sp hybridization, sp. Clear? Yes. Now this hybridizations you can connect with geometry also. Here one question is there with shape. Okay, shape. So if the hybridization is sp3 hybridization, the shape will be tetrahedral. Tetrahedral. Okay. And if it is sp2, it will be planar. Planar. Okay. Planar hybridization. I mean planar geometry, especially trigonal planar. Okay. Trigonal planar. And sp, it will be linear. Linear. Okay. Yes. So what is the first one? CH2 double bond O. Okay. So you have to find out the hybridization of this particular carbon. So you can see one double bond is there. Double bond is there. So what is the hybridization? That is definitely sp2 hybridization. sp2 hybridization. And what is the shape of the compound? What is the shape of the compound? That is trigonal planar. Okay, trigonal planar will be the shape of the compound. Clear? And second one, you can see one triple bond is there. Triple bond is there, that means that will be sp hybridized carbon, and the shape will be linear. Shape will be linear. Linear. Okay, linear, 180 bond angle, 180 degree. Okay, so that's about that question. I think it's clear. So we can move to the next one. I hope all of you are getting clear. Yes. Next one is a nomenclature question. So we can name in the question itself. So bond line formula is given. Bond line formula is given. You have to name the compound. Can you please tell me what is the functional group present in the first compound? Functional group. Functional group is this one. This is the functional group. What is that? That is an aldehyde group. Aldehyde group. C double bond OH or CHO. That is aldehyde group. So definitely you have to start numbering from that aldehyde carbon. Okay. So 1, 2, 3, 4, 5. And one methyl branch is also there. Methyl branch is also there. So what is the name? What is the name? 4-methyl. 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 What is the word root? 5 carbon atoms are there. So pentanol. Exactly, it is pentan-1-al. Pentan-1-al. Clear? Yes. Okay. So we can move to the next one, B. So here a cyclic structure is given. So definitely you know here CH3 groups are there, methyl branches are there. Methyl branches are there. So you can give number to this carbon as 1 and to this carbon as 2. Okay, and one double bond is present. Double bond is present. What is this ring exactly? How many carbons are there in the ring? 5 carbon. So definitely a cyclopentane ring. But here one double bond is there. So cyclopentane. Okay. So how you can start the nomenclature? By mentioning the branch. Okay. So 1,2 dimethyl. 1,2 dimethyl cyclopentene. Cyclopentene. Okay, that's the name, cyclopentene. I hope it's clear. Okay, yes, good. So we can move to the next one. Okay. You have to draw the structures of these compounds. Draw the structures of this compound. First one, pent-3-enoic acid. Pent-3-enoic acid. So always if a question comes like, if they give some names and you have to draw the structure, always mark the word root first. Okay, pent. Okay, in second one also it is pent, and third one it is, okay, that's a cyclic compound, I mean aromatic compound. Okay, so we can do the first one, pent-3-enoic acid. So draw 5 carbon atoms first because the word root is pent. Okay, so 1, 2, 3, 4, 5. What is the functional group here? Oic acid. Oic acid. So definitely one carboxylic acid group should be there. Okay. So C double bond OOH. C double bond OOH. Okay. Then pent 3-ene. 3-ene means on third carbon one double bond is there. Okay. So which is the third carbon? You have to start numbering from this side. 1, 2, 3, 4, 5. Okay. So on third carbon means you have to make the double bond here. Okay, like this. Okay, so now you can fill with hydrogens, CH3, CH, CH, CH2, COOH. Got it? Clear? So this is pent-3-enoic acid. Pent-3-enoic acid. Okay, so we can try the next one. 4-methylpentanone. 4-methylpentanone. So again 5 carbons. So 1, 2, 3, 4, 5. Okay. Which is a functional group here? Functional group is ketone because pentanone. Pentanone. Okay. So C double bond O. I think you know that ketone group will be always present in the middle of 2 carbon atoms. You can't place a ketone group at the end. Okay. So you have to start the numbering from this side. 1, 2, 3, 4, 5. Okay. 4-methyl. 4-methyl on 4th carbon, 1 CH3 group. Okay. Then you can fill with hydrogen. CH3, CH, CH2, CO, CH3. Okay. Clear? That is 4-methylpentanone. Okay. Now we can do the last one. Yeah. 4-ethyl 3-fluorophenol. Okay. So I hope all of you know the structure of phenol. Okay. It's a very important compound which is involving in organic reactions and all. So this is phenol. This is phenol. So 4-ethyl, which is the first carbon? This is the first one. 1, 2, 3, 4. So 4-ethyl. On fourth carbon, one ethyl group, C2H5. C2H5, or you can write CH2CH3. Okay. And 3-fluoro. So on third carbon, one fluorine. That's it. Clear? Yes, good. Okay. So that's about that question. Now we can move to the next one. I hope this one is very clear, very perfect. Coming to the next one, draw the resonance structures of the following compound. Okay. Apart from this question, along with this one more part is there. You have to write the IUPAC name and yeah, it's here. Yes. So we can do this one first. Write the IUPAC name of the above compound and identify the type of resonance effect it will exhibit. Okay. So first of all, what is the IUPAC name of the compound? You know this compound is phenol, but phenol is not the IUPAC name. That is a common name. The IUPAC name of the compound is hydroxybenzene. Okay. Hydroxybenzene, because OH group is hydroxy group. Okay. Now identify the type of resonance. We have two types of resonance structures: resonance effect, plus R effect and minus R effect. If the electron pairs are coming down to the ring, that means if electron pairs are pushed towards the ring, that is called plus R effect, and if electron pairs are getting withdrawn towards the group from the ring, that is called a minus I effect. Okay. So here definitely you can see electron pairs are there in oxygen. That electron pairs will come down and participate in resonance like this. So definitely that is plus R effect. So you can write positive resonance effect or positive mesomeric effect. Okay, both are same. Clear? Okay. Draw the resonance structures of the following compound. Okay, so I am drawing here. Please listen. I hope all of you know how to draw these structures. Very important. So first, this lone pair of electron will come down. Okay, into this particular bond. So this will become double bond. So if this bond will become double bond, what happens to this bond? That bond will move to this carbon, that pair of electron. Okay, so you can draw the next one. So here it will become double bond. So OH, it will become double bond. Okay, then here one positive charge because that electron pair come down. Okay, so here electron pair is there, negative charge, and here one double bond and here one double bond. Clear? Now what happens in the next step? This electron pair will be shifted to this place to become a double bond. Okay, so at the same time this bond will be shifted to this carbon. Clear? So the negative charge is shifted to this particular carbon, para position. Okay, so I can draw the structure like this: OH, then double bond, so here one double bond is there already, and here one double bond, and here the negative charge. Clear? Now what happens next? This negative charge electron pair will move to this particular place. So at the same time this will move to this carbon. Okay. So you can draw the next structure, that will be like OH double bond. Okay. So here the negative charge will come. So here one double bond and here one double bond. Clear? Okay. And next one, what happens next? This will move to this particular place. So at the same time, this double bond, the electron pair in this double bond will move back to the original place. Okay, original place. So you will get the structure like here one double bond, here one double bond, here one double bond. Okay, and just wait. This double bond will not be there. Yeah. Okay. That's it. See what is the difference between the first structure and last structure? Both are phenols, but you can see the position of double bonds that are alternative. Okay. So in the first structure, double bonds were in this position, here, here and here. But in this one, it's an alternate. So that's why we represent phenol or organic structures like this by a circle in the middle. Okay, to indicate this resonance, because that pi electrons are moving, rotating inside the structure. Okay, that's called the resonance. That will make that molecule more stable. Okay, clear? Yes, good. So that's about this one. It's a very important question. You have to practice in your notebook. Okay, separately for this one. Then nitrobenzene, many examples are there. Okay, yes. I think we can move to the last question. Last question is related to isomerism. Define isomerism. What is isomerism? Isomerism is the phenomenon of exhibiting different compounds. Okay, two compounds with the same molecular formula with different structures and properties. Okay, different structures and properties. So they will have same molecular formula. Draw a flow chart and explain each type of isomerism with examples. Okay, so I will draw the flow chart here. Okay, listen. Isomerism. We can broadly classify isomerism into two types. Which are they? Structural isomerism and stereoisomerism. Structural isomerism means same molecular formula with different structures. Stereoisomerism means same molecular formula, but they differ in the spatial arrangement of atoms or groups. Okay. Structural isomerism you can classify into different types again. Structural isomerism can be again classified into chain isomerism. Okay. So chain isomerism, position isomerism, functional isomerism, then metamerism. Okay, so we can check examples also. Chain isomerism means, as the name indicates, their parent chain will be different. For example, butane. Okay, butane, CH3, CH2, CH2, CH2. Okay, butane. So what is the molecular formula of butane? C4H10, C4H10, and methyl propane. Okay, 2-methyl propane. So CH3, CH3, CH3. Okay, 1, 2, 3. 2-methyl propane. This is also having the same molecular formula C4H10. Okay, same molecular formula, but they have different parent chain. Here the parent chain is but, here the parent chain is prop. Okay, so they are chain isomers. Chain isomers. Okay, now next one, position isomerism. Position isomerism. Coming to position isomerism, position of the functional group will be different, but same functional group. Okay, for example, CH3, CH2, CH2OH. Okay, propanol, exactly propan-1-ol, 1, 2, 3, propan-1-ol, and CH3, CHOH, CH3, 1, 2, 3. Here you can see the OH group is on second carbon, but here on first carbon. So this is propan-2-ol. So they have same molecular formula, but different positions of functional group. So they are position functional group. Sorry, position isomers. Okay, position isomers. Clear? Yes. Next one, that is functional isomerism. Functional isomerism. So definitely they'll be having same molecular formula but different functional group. We can check. Okay, so CH3, C double bond O, CH3. What is this compound? Acetone. Okay, propanone. Okay, propanone. What is the molecular formula? C3, C3H6O, C3H6O. Okay, and what is this compound? This is propanol, an aldehyde. What is the molecular formula? 3 carbon. So C3, how many hydrogen? H6 and 1 oxygen. So same molecular formula but different functional groups. So functional isomers. And next one is metamerism. So metamerism exists in a case where on both sides of the functional group different alkyl groups are attached. So especially in ethers, I hope all of you know, ethers are like this, ROR. Okay, so for example, CH3, CH2, O, CH2, CH3. So this is an ether. Okay, diethyl ether. Clear? So next one, CH3, CH2, CH2, OCH3. Clear? So this is another ether. So what is the difference here? You can check. In this one, these are the alkyl groups attached on either side of the functional group. But in this one, these are the alkyl groups on either side of the functional group. But both of them have same molecular formula. So this type of structures are called metamers. Okay, and the isomerism is called metamerism. Okay, I think it's clear. So Coming to stereoisomerism, about stereoisomerism you will learn in chapter hydrocarbons in detail. Okay, so here you just need to mention, clear. Stereoisomerism can be classified into geometrical and optical isomerism. Geometrical and optical isomerism. So I will just give you the names of the compounds, I mean details of the classes. Okay, details of the classes. Okay, listen. Geometrical isomerism, there are two types: cis-trans isomerism. Cis-trans isomerism. Cis-trans, that is geometrical isomer. Okay, cis and trans. This is based on rotation about a double bond. Okay, rotation about a double bond. And optical isomerism is based on optical activity of substances, and there are two types: dextro and levo. Dextro and levo. Dextro, that means D or a plus sign. Levo means L or a minus sign. Okay, that's it. So you will learn in detail about this isomerism in hydrocarbon chapter. Okay, so I think it's clear, very clear about these questions. So all these are very important questions. Okay, you can expect for your board exams and all. Clear? Yes. So we can solve a different question paper in the next video. I hope all the concepts are clear. Okay, you can suggest your opinion and your topics, like which topic you need next, you can put in comment box. Okay, I hope all of you understood well. Okay, clear? Okay, then we can wind up now. Bye, take care all.